Kia ora Year 11 and 12. This video is for Harry and it's a question from the Specimen paper and it's quite a nice geometry problem. It's got two parts. The first part is pretty easy and the second part will make you think a little bit harder. So we've got two circles and we should always read these questions really carefully. This one gives you all of the information in the words, but sometimes you have to think about what's in the diagram as well. So the first circle is the little one and it's got a centre at A and a radius of R. So here's the centre and there's the radius. And the diameters CAD and BAE are perpendicular to each other. Then we've got a bigger circle, and that goes through points C and D. The first thing we have to do is to show that the radius of the larger circle is R root 2. That's going to lead us into solving the second part of the problem. So let's just draw on it what we've got. We know that this is a radius, right? We know that A is the centre and that B is also on that circle. So that means that the second side there, AB, also has length R. And then here, from the centre of the big circle, B, to the circumference, C, is the length that we're looking for. And you can see that what I've drawn out there is a little right-angled triangle. So let's draw that now. We've got A, C, B, and we've got an angle here, and this is R, and this is R. So AB is equal to CB is equal to R. And by Pythagoras, we have this. So CB squared is equal to A squared plus B squared, R squared plus R squared. So length CB squared is equal to 2R squared, which means that length CB is equal to the square root of that, which is equal to root 2R as required. All right, so radius of big circle is CB. It probably would have been good to say that at the start. Okay, so that's the first part done. Now for the second part, there are at least two ways to do it, and I'm going to go through both of them in this video. I'm going to do that because quite often you're not going to see the most efficient way. So the first way that I'm going to do is not the fastest, and it's not even the cleanest, but it's a place that we can get to using quite simple geometry things. The only thing that you probably will have forgotten and might not have revised yet is the formula for the area of a segment. Now you're not given that one on the formula sheet because the area of a segment is just the area of a sector, take away the area of this triangle. So the formula for the area of a segment is 1/2 R squared theta minus sine theta. The area of a sector is definitely going to come in useful here, and that's 1/2 R squared theta. Remember that we have to have all of our angles in radians for these to work, for anything with circular measure. Other useful things that you don't need for this problem are the arc length, right, which is S is equal to R theta. That comes up a lot. The area of a triangle, which is either 1/2 base times height or 1/2 AB sine C. Now we will probably use that one in here when I do this the second way. So let's go back to the clunky way to do this. I always find it best to draw a pretty slow diagram with problems like this one. So in this case, what I'm looking for is the area of the whole of the little circle minus a couple of bits of it. So which bits don't I want? Well, I can divide that up into a sector and then these two little bits here. So the first way that I did this problem was to find this and then take away the area of the sector and then to take away the area of two small segments. So I'm drawing on my diagram now. This is the area of the sector that I want to remove. And then I also want to remove this red bit here and this red bit here. So let's check if we're going to be able to find those red areas. Well, you can see that we are, because there's segments in the little circle. Okay, so that's the first way that I'm going to do it. Now I'm talking really slowly on purpose because I think that the breakdown of how we do these questions is by far the hardest bit. So let's see what we've got. So we've got area of circle minus area of sector BCD minus 2 times segment ABC. All right, so I'm labeling those using the point. So here's segment ABC here. Some of you will be groaning and going, wow, there's a much, much easier way to do this. So what's the area of the circle? Which circle am I looking at? Well, it's just the little circle, right? So the radius is r squared. Now, when I do my working in questions like this, I separate the bits out first. So the area of the circle is pi r squared. Okay, now what about the area of the sector? Let's go back up to the diagram and see what's forming that sector. Well, the sector's being formed by the big circle. Right? The sector that I'm trying to find has got a centre point at B, and then it's this. So the radius that I want for the sector is the radius of the big circle, not the little one. And I also have to think about the angle in the big sector. So what's the angle here? Well, we know that it's 90 degrees. Okay, there's two ways that we know that. We know that from the first part of the question where we had that little triangle that I'm drawing on had a 90, was an isosceles, right? Because this is R and this is R, so they must each be 45, and that means that that one must also be 45. But we also know that it must be 90 degrees because angle BCD is the angle in the semicircle. So that means for the sector, my formula is half r squared theta, right? So here, it's equal to a half times root 2r squared times pi on 2. When I simplify that, I get 2r squared on 2 times pi on 2, which gives me pi r squared on 2. Now let's do the last bit, the area of that little segment. Well, the little segment is a pretty easy one to get. It's coming from here out to here. So the angle theta there is 90 degrees. And my radius is r. So the area of segment ABC is equal to a half r squared times theta, pi on 2, minus sine theta, sine of pi on 2. And we know that sine of pi on 2 is equal to 1. So the area of that segment is a half r squared times pi on 2 minus 1. And we want 2 of them. So that's going to equal r squared pi on 2 minus 1. So now we're nearly finished. What we have to do next is to take the area of the circle and subtract off those two things. So the shaded area is equal to pi r squared minus pi r squared on 2 for the sector minus r squared times pi on 2 minus 1. That gives me r squared into pi minus pi on 2 minus pi on 2 plus 1, which gives me a final answer of r squared. So that's how I did it. Now, the other way that you can do it, which is much, much more obvious, and most of you will be screaming at this point, why did she do it that stupid way, is to look again at that shaded area. So I'm going to erase all of this. The other way that I can do it is to say that that shaded area is the area of the semicircle in the small one minus the area of the segment of the big one. So if I do it that way, I get a half pi r squared minus the area of this segment, right? And again, we have to find that angle there, but we know that that's pi on 2. So it's minus a half the radius of the big circle times pi on 2 minus sine pi on 2, which gives me a half pi r squared minus r squared times pi on 2 minus 1, which gets me pretty quickly to r squared. So there you go, 2 ways to do the same question. Thanks for watching. Keep on sending in the questions. I'll have a little bit of time late this morning and maybe later this afternoon. Harry, if you're watching this, I'm going to do your trig proof one next.